get started. So I'm really grateful to be here today. I'm presenting the Lookahead Optimizer. I had great co-authors in James Lucas and professors Jeffrey Hinton and Jimmy Ba. So let's just dive in. So first, let's take a step back and try to understand why optimization matters. So it really shows up in all over the place in machine learning. And we can broadly speak about optimization problems and optimization methods. And one big challenge is in just formulating the optimization problem itself. So Stephen Boyd at Stanford does a really great job of characterizing how to look at different abstractions in optimization. And one way you can think about this is when you have a new machine learning problem, you typically first look at the data set you have. And this can be like whether or not the data is labeled, whether you're doing classification for regression, and how much data you actually have. Once you have a better understanding of your data, you typically go about building your model. So this could be like a linear or quadratic model, or it could be something like a neural net or a decision tree. After we formulate the optimization problem, we typically have some sort of variables we're trying to optimize over, constraints, and an objective function that we're trying to minimize. And then depending on the problem, we choose a method to optimize the problem. So in the case of linear objectives and linear constraints, we can actually solve the problem exactly with something like a convex optimization solver. But for something like deep neural networks, we have to resort to methods that, rather than solving it directly, we take gradient steps to solve and minimize our objective. So this categorizes problem approaches such as gradient descent, Adam, or more recently, the paper I'll be describing, the Lookahead Optimizer. So I guess broadly speaking, most of the approaches to improve optimization these days can be categorized into adaptive momentum methods, where you have a momentum that accelerates the direction you're going towards based on your gradient, and methods like Adam, which have a different learning rate for each direction of your parameter space. But Lookahead is sort of orthogonal to both of these directions, and I'll start by describing some of the related work. So the idea of Polyak averaging, proposed by Polyak and Rupert around 1992, is the idea of taking the arithmetic average of your weights. And this is shown to give better convergence guarantees in convex optimization. So when your loss service is really nice, if you average the weights throughout optimization, you can get faster convergence. And this is an idea that's seen in the convex optimization community, but hasn't really seen more attention in neural networks until more recently. So one instantiation of this approach is the stochastic weight averaging paper from 2018. So the idea behind this paper is, in traditional methods, you typically create an ensemble by averaging the predictions of different models you've trained. But stochastic weight averaging is saying, rather than averaging the predictions, we can instead average the weights of your neural network. And this turns out to beat existing methods of ensembling methods in model space. And they have some nice visualizations showing that if you average the parameters at different points in training, you can get better test accuracy and typically lower training loss. So what we can see is some of the intuitions from these visualizations later on as well. One other related paper is the regularized nonlinear acceleration. So the idea behind this paper is you're also doing some sort of look ahead by taking different steps forward. And roughly speaking, the point you want to find is a point where the gradient is 0, because that corresponds to a local minima or a saddle point, which is not as good. But so they try to approximate this by looking at the most recent k iterates, looking at the difference between them. That's a proxy for the gradient. And you can solve a system of k variables and k equations, k unknowns, which is k times the amount of memory for one gradient. And if you do this, you can sort of get an approximation for where the minima should be. So this is similar to our method, but it's on the order of k times more memory. So this is related work, and now we'll get into the description of the Lookahead Optimizer itself. So the way Lookahead works is we first have to wrap around an inner optimization algorithm, such as stochastic gradient descent or Adam. And what we do is we initialize our neural network as usual from some random initialization, and we'll term this the slow weight. So we save the slow weight for later, and what we do is we take in many batches of data and update our parameter using the standard optimization algorithm. So we'll take a step based on SGD or Adam, and we'll continue like this for k steps. So in this case, k is going to equal 5. And once we hit this point, what we do is we look at our save point and the point we are k steps into the future, and what we do is we linearly interpolate in parameter space along this direction. So this looks something like this, and you go in this direction by some factor alpha. Once you do this, you save this as the new slow weight, and then you continue for, so this is a one step back, and then you take k more steps with your inner optimizer, like SGD or Adam. So it looks something like this. And then once again, we interpolate in parameter space. So you can add notation based on like which inner and outer iteration you are in, and we can also write this out more formally in pseudocode. So I guess the key thing here is, in addition to the standard optimization algorithm, we are also introducing 2 additional parameters in the form of k, which is the number of steps, Lookahead steps you take, and alpha, which is how much you interpolate in parameter space. So one thing to give us a bit more intuition into why this sort of update might help is we can do a projection of this high-dimensional neural network space, which can be something like 8 million parameters for a ResNet, into a 2D plane. So the way we do this visualization is we look at 3 points along the trajectory. So we take the first, the kth point, the final point, and a middle point. And we look at the difference between like this second point and the first point. That defines a vector. And then we also look at the difference between the third point and the second point and remove like the part explained by the first vector. This is sort of like the Gram-Schmidt process, and that defines another direction. So we project everything onto these 2 directions, and what we can do is visualize the test accuracy along these 2 contours. So what we can see is that as you take the k steps forward with your inner optimization algorithm, you're actually at a region of lower test accuracy, but along this interpolation direction, we get a region of higher test accuracy. And if you continue forward with SGD, you're again like sort of circling around the minima, whereas if you do the Lookahead step again, you get to a region of even higher test accuracy. So this might sort of suggest that at some point in neural network optimization, our surface is almost potentially convex, but there are also artifacts of projecting such a high dimensional space into 2 dimensions. So you can interpret like the test accuracy exactly, but not necessarily like the trajectory itself based on the projection. And we'll also do some like analysis with math using a model that has seen recent work from like James Martins or Roger Gross. And the idea here is that because a neural network is sort of hard to analyze analytically, we want a simple model that can serve as a proxy for neural network optimization. And it turns out a simple noisy quadratic model can do pretty well. So the idea here is that we model the loss surface of our neural network using a quadratic loss. And rather than assuming we have the true gradient of the loss function, we instead assume we have a noisy version of the gradient. So we get the true gradient plus some Gaussian noise. And it turns out this model can actually do a really good job of modeling the stochasticity of neural networks. It might not capture behavior like having 2 different minima, but it does a good job of modeling like the effects of batch size. So I'll point to like a recent work by Guodong Zhang that he's done recently using this noisy quadratic model. So there was this paper that came out last year that showed that in terms of analyzing batch size, so I guess if we take a step back, the reason we might want to scale off batch size is if in industry you have a lot of compute, you can potentially paralyze the training of a neural network by using multiple computers and putting like mini batches, splitting up your mini batch and accumulating all the gradients. And sort of what we want is we'd hope that using a large batch size would get us to a solution of higher quality earlier. And indeed, if you look at these sort of graphs, we have batch size on the x-axis and steps to a particular target validation loss on the y-axis. These are a bunch of common data sets across the different domains. So what we see is that in the regime on the far left, you can achieve this near perfect scaling where if you double the batch size, you take half as many steps to reach a target loss. So this is essentially saying if we have twice the amount of compute and we're in this regime where batch size is perfectly scalable, we can just double our batch size, double our compute, and we get our final solution in half the amount of time. But eventually, you don't get this perfect scaling. You get a diminishing returns region, and eventually it flattens off because for large batch sizes, we don't get any more gain from getting a better estimate of the gradient. So the surprising thing is, like, if you do this noisy quadratic analysis on this particular problem, you can find you're able to predict the effects of batch size scaling. So you can, in fact, tell like at what region the batch size scaling tails off. So this suggests the noisy quadratic model is pretty useful in these settings. So returning to Lookahead, what we can show is that if we use the same learning rate, Lookahead turns to reduce the steady state variance of the noisy quadratic model. And we can, basically, the variance of using stochastic gradient descent gives you some fixed amount of variance. And if you apply Lookahead using the SGD as the inner optimizer, we get this term at the beginning that's less than 1, so the final steady state variance is lower. So we'll get to a solution of higher quality intuitively. You can see this through simulations as well, where we show like the expected loss you're able to achieve and what loss you achieve by actually rolling forward through the noisy quadratic model. So this is sort of like a framework for simpler analysis. But I guess the rest of the talk will dive more into experiments on actual data sets and talk about these results. Okay, so the first experiment is on CFAR10, which is an image recognition data set so for all these experiments, we consume the same amount of data for every single optimizer. Since Lookahead takes like k steps for each like outer update, we use k times fewer data, so all the comparisons are fair. And what we do is we find the best hyperparameters for the inner optimizer, such as SGD and Adam, and then we wrap Lookahead around the inner optimizer and evaluate its performance. So we can see here that Lookahead converges faster in terms of training loss on the CFAR10 data set. And perhaps more surprisingly, it's also very robust to the choice of inner optimizer hyperparameters. So if you take SGD and you scale up its learning rate, so like if you had a new problem and you aren't sure what the proper learning rate is on the problem, SGD can perform really poorly, especially in the early stages of optimization before you decay the learning rate. But for the Lookahead wrapped around the same SGD optimizers, we do much better in comparison if you chose a bad learning rate at the beginning. This is the same story with momentum, and it perhaps stands out a little bit more. And one complaint you might have is that perhaps we're introducing 2 additional hyperparameters in terms of k and alpha, and now we have to search over 2 hyperparameters as well. But we have an experiment on the CFAR100 dataset showing that for different Ks and alphas, we do better than the vanilla SGD baseline. So really, the variance reduction is giving you a lot of benefit in this picture. And I guess like one other issue that's worth mentioning is that for these research data sets, we kind of have like a standard way to decay your learning rate schedule based on like many, many experiments. But in a new data set, you might not know how long you want to train for, when to decay your learning rate. And having this better anytime performance is pretty important because you can just stop and like at any given time, our training loss might be much better than what like the vanilla optimizers have. And one final picture on the CFAR10 dataset that paints this variance reduction property is we can also evaluate the test accuracy of the intermediate points along the optimization trajectory. And what we see here is that the SGD updates actually can harm your test accuracy pretty significantly, while doing the interpolation with a Lookahead update restores your test accuracy. And this is more drastic when you look at like immediately after a learning rate decay, you'll see this effect where the intermediate updates decrease your test accuracy. Quickly going over lists, so stochastic weight averaging, people might say is a similar technique, but we show that our method is complementary to SWA in that if you combine stochastic weight averaging with Lookahead, you achieve a region of even higher test accuracy during this weight average ensemble of neural networks that I talked about earlier. We also have good results on ImageNet. So this is a huge image classification data set with over 1 million images, and we train our models with 50 million parameters on these. And you can see Lookahead gets a better training loss as well. So because the traditional schedule has a region where the training loss barely improves, we tried a more aggressive learning rate decay schedule where you decay the learning rate earlier, and we also see that the training loss improves faster using our approach. And we just used the same hyperparameters we found here, scaled it to ResNet 152, which is an even bigger model, and it worked in this setting as well. And even though in optimization, you typically focus on minimizing the training loss, it turns out that for the models we trained, a decrease in training loss is generally correlated with better test or validation accuracy as well. So on the left, you have the CFAR validation accuracies, and on the right, you have the validation accuracies for ImageNet. We also tried training our models on neural-machine translation. So here, we more or less achieved the same final training loss, but we see some improvements early on in training. So this is training the transformer models, which use self-attention on machine translation. And one final regime which we evaluate our model on is on language modeling. So in this task, your goal is to predict the next word in a sequence given the previous words. And here we also wrap Lookahead around the Adam optimizer. And the way our models are evaluated in this language modeling setting is we want to try to minimize the uncertainty about the next word we predict. So the higher the number you see there, which is the perplexity, the more uncertain we are. So we want a lower number, which means our language model is performing better. And we can see that both Lookahead wrapped around Adam and Lookahead wrapped around SGD do better than their vanilla counterparts. And we also achieve a better final validation and test accuracy as well. So to summarize, we basically introduced a new method that achieves faster convergence on a variety of different data sets and models. It's pretty robust to the choice of hyperparameters, and it's like really easy to incorporate into existing pipeline as well. In terms of extensions, it's interesting to see whether or not we can do some sort of learning rate scheduling, maybe even in terms of the alpha parameter within the Lookahead Optimizer, and then look at this general family of methods that maintain memory information. So Lookahead has one additional copy because we save the parameters every k steps, but we can potentially imagine other schemes for maintaining additional memory about the gradients. So to use our method, you can incorporate this into any existing TensorFlow or PyTorch pipeline with essentially 2 additional lines. You just have to use your existing optimizer and then wrap it around our wrapper, which takes in the number of Lookahead steps and the alpha for the slow weight interpolation. And our code is all currently online. So that's all I had. Thank you for your attention.
For the implementation you have, or for the algorithm itself, is it built in such a way that it can be parallelized for GPU learning, or is it just serial CPU?
Yeah. I guess if you use a framework that already supports parallelization, it should be able to handle things just as it is, because all we're doing is we're accumulating the gradient steps, and then every once in a while we pull them all together and then interpolate back to the previous step. Yeah.
Thanks, that was really interesting. So if I understand correctly, you're doing all of the k steps with the same batch of data, right?
We're actually sampling different mini batches.
Oh, okay, so everyone was a different mini match. Okay, that actually answers my question. Thanks.
Okay, yeah.
Yeah.
Thanks, great talk. I'm glad I have something to go play with now.
Yeah.
Thanks for the code. I have a question about the projecting into the 2D space. Do you have a way of evaluating that projection to minimize those artifacts?
Yeah, so it's potentially interesting to look at a search along this direction because it seems like you can optimize how far you want to go in this like projected direction, right? So we did some work with that, like trying to find like what the optimal choice of going this particular direction actually is. But in practice, it seems like choosing something like it's a fixed value does really well, and you might be like overly greedy if you try to like optimize this choice of step size. Yeah.
Hey, I think you just answered my question, but I was gonna say, like, what if you did something really drastic with taking just two, like, not K, but just 2 steps back an entire, like, algorithm? Have you found that to have a positive impact?
Oh, you mean like take 2 steps and then do it?
Just like, imagine you have 1,000 steps.
Yeah.
Like, go 250 and then go back.
Yeah.
In the middle, and just do that twice.
Yeah. It's possible, yeah. I don't know. It's hard to have a good intuition on these things until you try them.
Do we have more questions?
Thank you so much. It was really, really interesting for me. I have a few questions. The first thing that, did you consider the warm-up for all of the comparison you did?
Sorry, what about the comparison?
When you present the result and you made a comparison between different models, did you consider the warm-up for all of them or no?
The normal form?
The warm-up.
Oh, the warm-up. Yeah, so I guess for the transformer models, you need a warm-up schedule. For the other ones, you just have a standard learning rate schedule, and that's the one we follow.
Okay. And the other question is that, did you consider that the maximum number of dimension could be mapped to the 2-dimensional, what's that number, in fact?
Yeah. I guess because the direction we're projecting onto is always going to be the same as the dimension of like how many parameters we have. Like this method of projecting isn't dependent on how many dimensions you have. But one thing is like because we're projecting such a high dimensional space into low dimensions, you can get like weird artifacts potentially because it's not clear like what this projection's doing so much. Yeah.
Thank you.
I think we can get one more question.
Hello. I'm wondering, have you played around with sort of projecting to a higher level dimension, sort of like projecting to 3 or possibly 4 dimensions? Or was there like a specific reason why 2 dimensions was sort of your target?
Yeah, I guess 2 is the simplest. That gives you some intuition about the curvature, so like different level sets of loss surface. So it could be interesting, and I think there's work in doing projections of neural networks into like cool 3D visualizations. There's like a website called lostlandscapes.com or something that has like these cool fancy projections. But we haven't played with those so much.
Thank you. Another question? Okay, that would be the last one.
Right. My question is, so there are 2 inputs. I'm looking at your code.
Yeah.
So when you define the optimizer, there are 2 variables, steps and alpha.
Yeah.
How do you figure out what values you're going to use? I mean, are you doing some extensive search on both the combinations, or
yeah, so
what are the right values?
I guess for our experiments, we tried k equals 5 and 10 usually, and alpha is 0.5 or 0.8, and just the cross product, so 4 different combinations, and chose the best one. So it's pretty minimal. And from the CFAR experiments, you can see that like all the combinations did better than the vanilla setup. So I guess it depends on your problem, but it's worth just trying it with like some setting and seeing how it does.
Thank you, Micah.